Array of Engineers has developed an automated test controller that conducts automated verification procedures on electronic devices, hardware, and systems. The ATC is a rack-mountable unit that is designed for desktop testing applications for industries such as medical and defense. Based on the Xilinx UltraScale system-on-chip, the ATC is a highly versatile analog and digital data acquisition model. While the ATC is a viable product, customers have expressed interest in a more portable version with similar functionality. This portable version of the ATC will allow Array of Engineers customers to easily field test without having to transport the equipment into the office. Array of Engineers has requested the creation of a newer and more portable version of the ATC that, while having some reduced functionality, would add certain other features. The ATC Lite was developed with a ruggedized enclosure to ensure drop protection and is sealed from dust and water. The new design is less than 2/3 of the original automated test controller. An accompanying graphical user interface was also created that will allow users to easily verify incoming and outgoing data. Our team consisted of Team Captain Carmen Von Air, Benjamin Brown, Ian McDowell, Donald Peterson, Taylor Rieger, and Dominic Smith.
I'm Carmen Von Air. My focus was on the electrical specifications of this project. This included schematic and board design. One of the most challenging aspects of this electrical design was accounting for part shortages and finding the exact components that would meet all of the requirements. The largest changes to the original ATC included added LIN hardware and an updated digital to analog converter. The hardest part of this design was fitting all of the existing circuits and the new circuits onto a board that was 1/3 of the size of the original. This meant a lot of rerouting and making sure all of the connectors would have enough space to reach the enclosure connectors through internal cables, since the size of the enclosure is also significantly reduced. The size of the board ended up being significantly smaller and fits into a much smaller enclosure. Here we have our system on module, which contains the processors and the FPGA that run all of the peripheral hardware. The system on module connects through some high density connectors and snaps onto the board. This is broken out then to our GPIO, our different communication ICs, along with our DAC and ADC and 1553 transceivers. Here we have 2 high-density connectors that use a ribbon cable to connect to our circular military connectors, which then mount onto the enclosure. This connector here contains all of the GPIO functionality, and this one has our LIN, CAN, and RS-232 communications broken out. This also has our digital to analog converter outputs as well. On the back of the board, we have our analog to digital input, which then has some jumpers to change the attenuation based on the probes that are being used with it. We also have a lot of jumpers down here in order to change the GPIO voltage levels from either 5 volts or 3.3 volts. Our SD card holder holds the SD card that contains an image that automatically programs the system on module when the board is powered on. Once all of the programming is finished, the Ethernet can be plugged in here and connected to our graphical user interface, which is then used to configure the board as needed. We also have a USB input and our JTAG programming and UART connectors here. All the power circuits are on the top of the board up here. It was critical to determine how much all of the ICs would be drawing off of the power circuits. One of the significant differences from the original is that the ATC had a positive and a negative 12 volts going into the system. We only have a positive 12 volts going in, so we had to generate our own negative 12 volt rail for the high-speed op amps that are used for the ADC and the DAC. Additional rails that were created include positive and negative 5 volts, 3.3 volts, and 1.8 volts. A total current draw of the system with the system on module on the board is about 1 amp, which increases when more operations are being performed. Without the system on module, the board draws about 300 milliamps. Both of these current draws are within our specifications for our power consumption of the board.
My name's E. McDowell, and I was the mechanical engineer on the ATC Lite project. My team and I were tasked with developing a small and ruggedized autonomous testing controller for a possible military application. My role in the team was to develop the external hardware of the controller and make sure that all the specifications set by our sponsor company, the Array of Engineers, were met. The design I came up with ensures that the PCB board that my team developed would be able to carry out its task in any extreme environment that it may be subjected to. One of these environments that this controller is designed to withstand is extreme heat. All of the components used by the ATC Lite meet military specifications for the temperature of operation. This ensured that no matter if the controller was in extreme heat or cold, that it would be able to carry out its functions. Measures with heat management needed to be taken for the system on module that had the possibility of overheating during extreme operations. On the first ATC that was developed by the Array of Engineers, the system on module was known to run at very high temperatures. To overcome this issue that was taking place, the generated heat would be passively dissipated by the enclosure itself. This was done by placing the system on module directly to the aluminum extruded enclosure that had a built-in heatsink. Due to the small size of the enclosure, there was a worry about the operators possibly burning themselves on top of the enclosure. So, to prevent this, we applied an additional heatsink to the top of the enclosure to dissipate even more heat generated by the system on module. The system on module and subsequently the PCB itself making direct contact with the enclosure. This created a possibility for deflection on the PCB board to start to take place. These can be caused by shock from the system being dropped or vibrations acting on the enclosure. These types of deflections account for 20% of mechanical failures that take place on PCB boards. So, to prevent these deflections from taking place, a dynamic method of mounting was designed. This was done by securing the PCB board by a dampener system that was said to decrease the acceleration felt by the board by 200%. I've discussed a lot about the enclosure, so let's dive more into the details behind it. Array of Engineers wanted an off-the-shelf solution for their enclosure so that the cost of manufacturing would be passed to the supplier and subsequently have the ATC Lite be more profitable. So for this project, we worked with a company out of Japan called Takashi for supplying the enclosure for the ATC Lite. I sent them the CAD drawings for what needed to be machined and what labels needed to be added. What we received in return was an IP67 rated enclosure with silicone bumpers on the front and back panels. The IP67 rating means that the water and dust are unable to enter the system. Gaskets were applied to all the machine holes added to the enclosure for mounting and connectors to ensure that the IP67 rating was upheld.
Hi, my name is Donald Peterson. To connect the PCB to external devices, we had to create a breakout board. This breakout board would take these 70-pin high-density connectors and map them onto the 66-pin military circular connectors. From there, we were able to create some harnesses that would take the 66-pin military connector and map the one cable into the GPIO and GPIO as seen here, and the other cable would again using the same 66-pin military connector, but it would broke it out into the RS-232, the DAC, the LIN, and the CAN. So by doing this, we were able to successfully connect the PCB to external devices.
Hello, my name is Dominic Smith, and for the ATC Lite project, I was one of 2 people to work on the firmware. In the first semester, before we had anything set up, I was designated as the file manager, and this included me to set up the files on the Google Drive, as well as setting up the GitHub that we would later use in the project. Later in the first semester, I was tasked with creating the prototypes that we would use to test the new circuitry on the ATC Lite. This included the power circuitry, the new LIN chip, and the replacement DAC chip, where LIN is a communication protocol that automobiles use, and DAC is a digital to analog converter. After creating the prototypes in the second semester, I was tasked with actually developing the firmware. So this involved using Verilog and C for the drivers to design and implement the firmware. This would later be uploaded to the hardware that had been created and then tested to make sure that everything fits within the specs. One major part of the project that I worked on is the firmware, and on screen right now is the firmware for the DAC core. It consists of two parts. It's got a mode controller and a data controller, and I will be running a simulation to show how I ran tests and debugged the firmware throughout the project. Here I am running a simulation of the two modules on the DAC. The first one being the SPI communication module, and the second one being the voltage data control. To run these tests, I have a C file that exercises the drivers that I wrote, and this communicates with a file that acts as the registers on the firmware. This is a simulation because the firmware registers normally cannot be interacted with until you upload to the real board, so this software was very helpful for debugging before we were able to do that. These simulations were helpful because I'm able to look up close at the waveforms and match them to data sheets and specifications. A large part of the DAC is getting the signal to repeat itself with only one pattern input. And as you can see, the simulation allows me to look at the waveform and see that it's repeating over and over again. I can also make sure that the data clock pins and other related inputs to the DAC are aligned and everything is working properly.
This is Ben Brown, and I will be covering the GPIO portion of the firmware. So the GPIO portion of the firmware was split into two main categories. So there was the PWM as well as the arbitrary function generator. So the PWM functions as any normal GPIO PWM does. That is to say, you can give it a clock frequency as well as an on time, and it generates a simple PWM on whatever pins it's selected for. On the other hand, the arbitrary function generator works a little bit differently. It uses some basic commands that are loaded into a buffer, and it will read them sequentially in order to create a arbitrary function on the GPIO pins. An example of this could be something like being on for 2 cycles, turning off for 3, turning back on for 1 cycle, and turning back off for 4. Obviously that's a very simple example, but it's something that could be done with the arbitrary function generator. In a moment, I will show a simulation of both the PWM and the arbitrary function generator so that you can see an example of each. We'll start with the PWM test. So this test was a very simple test to show some functionality of the PWM and go through some basic setup and changing of the PWM. So as some background, how this works is that because this is testing a system on module that has a microcontroller and an FPGA, the firmware itself is not being directly written to, and instead the computer is acting as the microcontroller. So in this case, it is writing to a chunk of files that sort of act as like a bus between the computer and the firmware. Since the firmware is not being directly written to, how we go about doing this is to create a C file to modify all of these files and have the firmware running in the background just reading these files as though it was the input to the FPGA. So to begin, we can take a look at the PWM test. So by starting the firmware and running the PWM test, these files are being written to constantly. And once the PWM test is done, you can see that we get a pretty basic waveform, since this is PWM, where we start with something that has a long frequency and a very short on time, changing that to a short frequency and a long on time part way through. And there's also a little bit of a separation where we can see that some of the GPIO pins can change while leaving the other ones the same. This allows for configuration of each GPIO pin independently. So theoretically, every GPIO pin could be running a different wave. Obviously that's not very likely, but it gives the option. Next, we'll look at the arbitrary function generator test. This test is also a relatively simple test, filling the arbitrary function generator buffer with basic commands that are then read and producing a fairly simple output. So to begin, we will start the firmware and run the C code to modify the files as mentioned previously. And once this is done, we'll be able to see the buffer on the arbitrary function generator filling up with information, in this case, different commands and different data to write to the GPIO pins, and then the firmware actually reading through that buffer and writing to the GPIO pins accordingly. So now that the test is complete, we can stop the simulation, and we can see that it did indeed write correctly to the buffer. So the buffer here is getting filled up with, in this case, quite a few commands. The main thing to notice, there's no extra data to say whether or not the piece of data coming in is a command or is something to write to the GPIO pins. So instead, that is controlled by the last bit of, or I guess the first bit if you're doing most significant bit first, of information. So in this case, anything that starts with an 8 is a command. Here you can see that we only have one command, and that command is just the jump command. So we're jumping back to the very first piece of data as soon as we get to this jump command. So looking at this here, we can see that the buffer is filled up all the way until what is the 39th entry in hex. And then we can see that, if we zoom in a little bit more, that the arbitrary function generator is enabled and we begin reading. So if we look at it, we can see that we start from the very first entry and just work our way forward accordingly, all the way until we reach the 37th entry, which is the jump command, in which case the jump command is initialized and we go back to the first entry. This continues to loop throughout the rest of the simulation. The simulation is just long enough so that we can see a decent chunk of data come in. Now, what this looks like on the pins is obviously dependent on the function. In this case, we have it writing out ATC Lite in a pretty basic way. And you can see that every time the jump command is mentioned, it loops back through the process. So it writes it there, it jumps and writes it again. This is an example of an arbitrary function that could be generated using the arbitrary function generator. Obviously, it can be more advanced or simpler depending on the needs of the client, and is a fairly flexible way of creating functions in firmware.
The ATC Lite GUI communicates to the ATC Lite hardware through an Ethernet connection. On boot up, the ATC Lite GUI will display the connection screen. This will display the instructions for the Ethernet connection to be configured properly. Then, the user will type in the host and port number listed above to connect to the ATC Lite. This will then allow for the I2C, CAN, SPI, UART, and GPIO communication protocols to be available. The I2C, SPI, and UART are all housed within the low-speed serial screen because of the similar communication protocols within. All of these different transceivers are able to be configured so that each of them can have their own port. The information and data that is incoming and outgoing will be displayed on the table at right. Each screen also allows for user input or a file input. If the user has a CAN or a text file, the information can be uploaded so that the sending of the data can be performed much easier. Lastly, the GUI allows for a simple communication visualization so that the user can see whether the communication is completing properly. This includes the sending of messages, receiving of messages, and also the highs and lows of the GPIO chart that is displaying.
Thank you for taking the time to watch our presentation. We hope that you have enjoyed learning about the ATC Lite.